Hey you guys, here's your first video on chapter 4. I'm going to do the first couple sections for you in this video because chapter 4 is really long and it has a lot of information in it. So it's about aqueous solutions. Aqueous solutions are solutions that occur in a water environment where water either dissolves those things or doesn't. Now we have some, you can see below here, these are precipitates where they are insoluble in water, and that's why they're even showing up. In this picture, this is a water treatment plant, and water treatment plants, of course, whether it's wastewater treatment or water treatment, where water is made drinkable for populations, a lot of times it is chemically altered or treated before it goes out to the people. So water chemistry or aqueous chemistry is very important in water treatment. A solution is a homogeneous mixture of two or more substances where the solute is in the smaller amount and the solvent is in the larger amount. So examples of solutions are like a soft drink where water is the solvent and the solute can be sugar and carbon dioxide. Air is a solution. It's a gaseous solution where nitrogen is the solvent and oxygen and other things are the solutes. And a solid, even a solid solution is like solder, which is a mixture of two metals, where lead is the solvent and tin is the solute. This picture is showing you potassium permanganate, and this one looks a little bit more concentrated. And the more concentrated it is, that just means the more solute that's in there. An electrolyte is something that can conduct electricity when dissolved in water. A non-electrolyte cannot. So if it's a non-electrolyte, even though they're like sugar, there might be sugar down in here. And even though there's sugar down in here, it doesn't complete the circuit because it has no ions. A weak electrolyte has some ions, and acetic acid is a weak electrolyte that we'll talk about in the next slide. And then something that's very strong electrolyte, like sodium chloride, would do a lot more conducting and have more ions to conduct the electrons from one electrode to the other. So what conducts the electricity in solution? Cations and anions have to be there. For a strong electrolyte, you have 100% dissociation or dissolving, and 100% of those become ions. A weak electrolyte, not completely dissociated. So you still have a lot of this left over and only a small percentage of the ions that do the conducting. Remember that this is H3O+. Ionization, there again is acetic acid. That ionization is reversible. So a lot of it is in the form of acetic acid, and therefore it's a weak electrolyte. Hydration is the surrounding of each of these ions by water. So water surrounds ions based upon its polarity. So here's a positive ion. So there's a negative portion to water, and those negative portions are pointing themselves toward the positive. And over here, the positive are pointing towards the negative. That's hydration, where water molecules are arranged in a specific manner around a solute. Now let's see if we can show this video. This video is showing sodium chloride dissolving in water, but I don't think I can get it to play. So we are going to have to look at that in class. But either way, here's the chlorides and then here's the sodiums. And as you watch that, you'll see them be dissociated. A non-electrolyte does not conduct because it has no cations like glucose. So these are strong electrolytes which completely dissolve or ionize. Weak electrolytes incompletely dissolve, and do not ionize at all. And when I say incompletely dissolve, I mean incompletely ionize. And here's another video that we'll have to look at in class. For precipitation reactions that produce an insoluble solid. So when you see this happening, there's a solid show up, and that solid can have different colors. When you see everything in groupings like this, where the positive cation is with the negative cation, this is called the molecular equation. And you'll notice each one of the phase labels are here. The solid phase label is the precipitate, and if everything else is dissolved in water in its ionic form, ions floating around, then it is labeled with aqueous. So what our next one we're seeing here is called the ionic equation. Now each one of these have an AQ label, but if there's no label, you assume aqueous. But if there is something else, you label it as such. So this is called the ionic equation. And what just canceled out there were the spectator ions, and this is called the net ionic equation. So this is the equation that's showing you what is really happening, and that would be the yellow solid over here. Sodium and nitrate are the spectator ions. So as far as why this occurs and even how, this is a schematic of the water of these guys they were swimming around apart from each other, but as soon as lead and iodide find each other, they form a solid because they are insoluble in water, and the potassium and the nitrates would still be floating around. And there's that solid. So how do we know? Solubility is basically the maximum amount of solute that will dissolve in a given quantity of solvent at a specific temperature. Now, solubility, we are assuming in our table here, this is at 25 degrees Celsius. This table is showing you the rules, solubility rules for common ionic compounds. So there are some exceptions to these rules, and you won't find everything that you're looking for here. But in general, the soluble compounds are compounds containing alkali metals and ammonium. So there's no exceptions. So anytime you see Na with something else, it would be aqueous. Anytime you see NH4, which is ammonium, with something else, it would be aqueous again. All nitrates are soluble in bicarbonates and chlorates. So again, these are all no exceptions. But sometimes halides, a lot of times, are soluble unless, of course, they are buddied up with silver, mercury, or lead. So lead iodide that we saw in the previous slide, lead bromide, and lead chloride. Well, which lead are we talking about too? Are we talking about lead 2 or lead 4? Looks like we're talking about lead 2. Lead 2 iodide, lead 2 bromide, and lead 2 chloride are insoluble in water. This is called mercury 1, and mercury 1 chloride, bromide, and iodide are insoluble. But whereas mercury 2 is soluble. So the difference between mercury 1 and mercury 2 is Hg2+. So mercury 2 chloride would look like that, and that is soluble in water, whereas this one is not. So this could get into your water system and cause trouble, whereas if you buddied it up with this gun, which would be Hg2Cl2, that would be the formula for mercury 1 chloride, that would be insoluble and just go to the bottom of the ocean, if you will. And then I guess some bottom feeder might eat it and then have some mercury problems. But either way, it wouldn't be in the aqueous part of the ocean. Sulfates most of the time are soluble, unless, of course, you got that silver, mercury, and lead, but you also have calcium and strontium and barium in there that are insoluble. Most of the time, these guys are insoluble, unless, of course, they have alkaline metal or ammonium. And then most of the time, hydroxides are insoluble unless they are with barium. So if you saw barium hydroxide in an equation, the phase label would be aqueous. But if you saw any other hydroxides, unless of course it's an alkali metal, it would be solid. So here's I was already writing in there, but there's no exceptions. Now these were some examples of insoluble compounds, and the reason you're seeing them in there is because they're insoluble. These are all insoluble. Sulfides a lot of times are insoluble. Hydroxides are insoluble. That's what we saw in the previous chart. So if we do an example as far as classifying soluble or insoluble, is that soluble or insoluble? You look at your table and you find sulfates. Sulfates are generally soluble unless of course they're with silver. So that should be insoluble. How about calcium carbonate? Calcium carbonate, if you look at your table, carbonates are insoluble mostly, so calcium carbonate would be insoluble. Sodium phosphate, again, soluble. Why? Because of the sodium. Sodium makes everything soluble. To write a net ionic equation, first you write the balanced molecular equation, then you write the dissociated ions in there as cations and anions, cancel any spectator ions, check that charges and number of atoms are balanced. So let's try one. Silver nitrate and sodium chloride. This would be the molecular equation. Silver is +1. Nitrate as a whole is -1, like this. Sodium is +1. Chloride is -1. So when you want to write the possibilities that are going to occur, the positive goes with the negative, and the positive goes with the negative. So you see silver chloride is a product, and sodium nitrate. You go look at your solubility rules. All sodiums and nitrates are soluble, aqueous. Most of the time chlorides are soluble unless it's with silver. So now after you would cancel your spectator ions, and that they're nitrates and sodiums. So your net ionic would be silver plus chloride to make silver chloride. So that's a good template for you to follow to do any of these types of problems. Here's another example. Predict what happens when potassium phosphate solution is mixed with calcium nitrate. Write a net ionic equation. So what's going to happen? Positive is going to go with negative. Positive is going to go with negative. So you see we made potassium nitrate, but you had to change it. You have to be careful not to do this. You don't want to just bring that 3 over and put it like this, like transposing. This would be completely incorrect because as a formula for potassium nitrate, no, don't do that. So the goal is to kind of break it up into its pieces, and you see that potassium likes to be positive 1, phosphate is negative 3, calcium is positive 2, nitrate is negative 1. So when potassium goes with nitrate, you see there's a negative 1 and a positive 1. So they only need 1 of each. So you would see that in your formula. As far as calcium and phosphate, calcium is positive 2 and phosphate's negative 3. So you're going to need 3 calciums and 2 phosphates to make positive 6 and negative 6 and make it work out as far as making an overall charge of 0. So this is what you're seeing here. This was your molecular equation. Now we're seeing the complete ionic equation and then the net ionic equation. So your spectators here look to be potassium and nitrate. And then you're left with phosphate, calcium, calcium phosphate, which was insoluble. And there's a picture of it. It's a salt white solid. So I think that's the end of this installment of the PowerPoint slides for Chapter 4. So your fun sheet then has some questions on this. So go ahead and try those and see if you can answer those based upon what you've learned so far.